Hello sir, I am Rubin Bhattarai and our presentation is on Hadoop HDFS, a powerful technology built to handle modern data. To begin, I'll define the core problem that Hadoop was created to solve, which is big data. So what is big data? It is the data that is so massive and complex that our traditional tools cannot handle it. Think of it in terms of three main characteristics, which is scale, speed and complexity. These three characteristics can be defined as the three V's of big data. First, volume. It's the most obvious. It is the sheer size and scale of the data. Second is velocity, which refers to the speed of its creation. Data isn't just sitting in a database anymore. It's flowing in from sources in real time like a constant stream. And third is variety. In the past, data was structured. It fit neatly into rows and columns. Today, over 80% of data is unstructured. It's messy and mixed. You can't put video in a spreadsheet, and that's the problem. This graph tells the whole story. For years, businesses dealt with structured data, which grew predictably. But as you can see from the orange line, unstructured data is exploding exponentially. To put this into perspective, the New York Stock Exchange generates over 1 terabyte of new trade data every single day. Our old systems were built for the flat blue line, not this new explosive curve. And this isn't just a tech problem, it's a business problem that impacts every major industry. In e-commerce, it drives recommendation engines and fraud detection. In finance, it's essential for modeling risk and performing trade surveillance. Telecom companies use it to monitor network health. And in healthcare, it's powering breakthroughs in areas like gene sequencing and drug safety. The challenge of big data is massive, complex and universal, and it demands a fundamentally new approach. Next, I'd like to invite Swarnim to introduce Hadoop as the answer to big data.
Thank you, Rubin. Now that we have established the challenges of big data, I will introduce the solution using a real-world case study. Let's analyze the case of Sears. They were operating on a traditional data analytics architecture while they collected vast amount of data, about 2 petabytes. Their BI system could only access a fraction of it, around 10%. The remaining 90% of their high-fidelity raw data was relegated to archives. This results in what's called premature data death, where potentially valuable information becomes inaccessible and unusable. To overcome this, Sears transition to a Hadoop-based architecture. Hadoop provides a unified layer for both storage and computation. By deploying a 300-node Hadoop cluster, they achieve 100% data availability for processing. Instead of moving data to a separate compute grid, Hadoop brings the compute logic to the data. This allows for deep data exploration and advanced analytics on the entire dataset, unlocking its full value. So why a distributed system? Let's discuss why this distributed approach is so effective. A single monolithic server processing a terabyte of data becomes a bottleneck by its I/O channels. The processing time is limited by how fast one machine can read its disks. Hadoop, however, implements a distributed file system. It partitions the data and distributes it across many machines or nodes. When a job is run, it's processed in parallel across all nodes, enabling extremely high throughput. As the example shows, what takes one machine 45 minutes can be done in under 5 minutes with a 10-node cluster. So what is a Hadoop? Hadoop is an open source framework designed for distributed computing. It has two core components. First, the Hadoop Distributed File System, or HDFS, which provides scalable and fault-tolerant storage. Second, MapReduce, which is the programming model for distributed processing. A key principle of Hadoop is that it's designed to run on clustered of inexpensive commodity hardware, making large-scale data processing economically viable. So next, Pranaya will provide a more detailed background of Hadoop's architecture and its ecosystem. Thank you.
Thank you, Swarnim. Now that we have seen why Hadoop is a solution, let's take a look at its architecture. Hadoop isn't just a tool, it's an entire ecosystem that works together to handle big data. At the base is HDFS, the Hadoop Distributed File System, which stores all the data. This is where the large data sets are split into blocks and distributed across many machines. About HDFS is a MapReduce framework at Hadoop's main data processing engine. To bring data into HDFS, we use tools like Fume for unstructured streaming data and Scoop for importing structured data from databases. Once the data is in, the higher level tools helps with analysis. Hive support SQL-like queries, Pig enables data flow scripting, and Maout provides machine learning features. But today we'll focus only on the core of Hadoop, HDFS, and MapReduce. The Hadoop uses master-slave architecture and is divided into two main functions: storage and processing. For storage, we have HDFS. The name node is the master node. It keeps tracks of where the data is stored. The actual data resides on the several machines called data nodes, which acts as a worker. For processing, Hadoop uses MapReduce. The job tracker is the master component. It manages and assigns work. It splits tasks and distributes them into task trackers, which are the workers that performs the actual computations. So Hadoop has one master for storage and one for processing. They coordinate with their respective workers. Uh, now let's take a closer look at how HDFS manages storage. The name node is the central controller of a system. It stores the metadata about files, their names, locations, and structures. It does not store file contents, but only the map where everything is. The data node are the machines that holds the actual data blocks on the local drive. They also stay in constant communication with the name node. They sense the heartbeats to show that they are active, and block reports to inform the name node of the data that they hold. This regular communication keeps the system reliable and synchronized. On the processing side, MapReduce is the framework that runs data computation. The job trackers act as a main controller. When a job is submitted, it splits the job into tasks and assigns them to task trackers. The task trackers are the workers that perform these tasks. One major advantage of these setups is data locality. Each trackers often run on the same machine as a data node. So instead of moving data across the network, Hadoop moves the computations to where the data already exists. This design keeps Hadoop fast and scalable, especially for large datasets. Up next, Adarsha will explain the role of each SDFS daemon. Thank you.
Thank you, Pranay. Now that we have seen the high-level architecture, let's now take a deep dive into the specific role of the three key daemons that make up the HDFS: the name node, the data node, and the secondary name node. First of all, we have the name node. This is the master controller, the brain of the entire file system. It is primarily responsible for managing the file name system namespace. This means it can control the entire directory, structure, file names, and permission. To do this, it stores all of the system metadata in its main memory for a very fast access. This metadata includes all the list of files, the blocks that comprise each file, and most importantly, the location of all replicas for each block. Finally, it acts as the coordinator. It receives a constant report or heartbeats from the data node and then serves block locations to client when they need to read or write data. Now, our data nodes. These are the steps in the architecture and the true workflow of the cluster. They store the physical data blocks on that local disk drives. When a client needs to write data, it communicates directly with the data node to serve or receive those blocks. Data nodes are also responsible for executing replicant tasks. When the name node determines that a block is under-replicated, it will instruct a data node to create a new copy. To ensure that a name node knows a cluster is healthy, each data node sends a periodic heartbeat every few seconds to signal that it is alive and functioning correctly. Now about this brings us to our third component, the secondary name node. Its job is to be a housekeeper. Here's how it works. The names record each file system changes like a create, read, or delete into a transition log called the edit log. Over time, this log can be very large, which will slow down the name node's startup time. To prevent this, the secondary name node periodically performs a checkpoint. It downloads the last file system snapshot known as FS image in the current edit log from the name node. Then it merges those two files into a new compared FS image and uploads it back. This process keeps the edit log small and ensures the name node can restart quickly if needed. Now, so to summarize this, the name node is the master that manages metadata and handles orchestration. The data node is the slave that manages physical data blocks and provides storage. The secondary name node is a helper that manages checkpoints and perform maintenance. It's vital to remember that the secondary name node does not provide high availability or automatic failover. Its role is to prefer housekeeping and add in recovery. Understanding this distinct role is keys to understanding HDFS. Now Ajit will explain how these components work together during an actual file operation. Thank you.
Thank you, Adarsha. Now that we understand the rules of HDFS components, let's see how they work together in action. Let's talk about a file write operation first. First, the client contacts the name node and issues a create request. It's like asking for permission to create a new file. The name node then performs permission checks, and if successful, it creates a record in the namespace. Then it responds to the client with a list of data nodes. Finally, the client begins streaming data, but only to the first data node in the list. Uh, this is the start of the write pipeline. This data node stores the block and forwards it to the second data node, and then it forwards it to the third. This pipelining is highly efficient for creating replicas. Let's talk about the file read next. File read is a bit simpler. First, the client contacts the name node with an open request for a specific file. It then checks its metadata and returns the locations. The locations are the list of data nodes that hold the blocks for that file. For each block, it provides a list of all available replicas. The client then directly connects to the nearest data node to read the data block. The key takeaway here is that the name node orchestrates the operation, but the actual data transfer happens directly between the client and the data nodes. This prevents the name node from becoming a bottleneck. Let's talk about replication and rack awareness next. Fault tolerance is a core feature of HDFS and it's achieved through replication. By default, every block is replicated 3 times, but how HDFS places these replicas is critical. It uses a rack-aware placement policy. The first replica is placed on a node within one server rack. The second replica is placed on a node in a completely different rack, and the third replica is placed on another node, but within that same remote rack. This strategy provides protection against both a single node failure and a catastrophic failure of an entire rack, such as a power outage or a failed network switch. Now let's talk about what happens if a block becomes corrupt on the disk. HDFS is an algorithm that ensures data integrity using checksums. When a client writes a data block, it also computes a checksum. A checksum is a small unique signature for that data. It is created using an algorithm like CRC32. This checksum is stored alongside the data on that data node. Later, when a client reads that block, it also retrieves that checksum. Uh, it then recomputes the checksum on the data it received and verifies that it matches the original one. If the checksums do not match, the block is considered corrupt. The client then reports the corruption to the name node and simply requests to read a different uncorrupted replica from another data node. This process is automatic and ensures that the application always receives valid data. That is it for me. Now, Sauhardha will discuss how you can configure the system in the real world. Thank you.
Hi everyone, I am Sauhardha Kafle, and let's learn about Hadoop deployment modes. Here we have a standalone mode, pseudo-distributed mode, and fully distributed mode. In the standalone mode, it is used for development and testing, and it runs on a single JVM, and no SDFS or daemons are present here. And in the pseudo-distributed mode, all daemon runs is a separate process, but it will run inside a single machine, so it is used for simulation. And next, the fully distributed mode, it is used in the production environment. Daemons runs on a multiple machine, offers a real parallel task and fault tolerance. Next slide. Typical cluster hardware, we have name node and data node. Name node is a master node, data node is a slave node. Name node, it requires high RAM is because it holds all the metadata in the memory. It also requires high powerful CPU for processing client requests, and this is not much important here. And in the data node, which is also a slave node, this is actually for storing purposes. It requires less RAM and CPU, but it requires high hard drive, large hard drives. Next, the core configurations are core site XML, HDFS site XML, mapped site XML. Core site XML, it contains system-wide setting that is a name node, for example name node URI. And in the HDFS site XML, it contains the HDFS specific configurations, example replication factor, data block storage, path, etc. And in the map read site XML, it is for the map reduce functionality, and we must set it to use a yarn engine for the better for extra usefulness. And in the next slide, defining the cluster and the environment, we have master, which lists the master node like secondary name or name node, and in the slaves or workers, it lists the worker nodes like data nodes, node managers. And in the Hadoop environment, the TSS, which is a bash file, it is a script file to get a critical environment variables like Java home. The Java home is a path to the Java installation on our machine, and it also can tune heap size and memory for the demos. Let's see the implementation of the pseudo distributed system. I have actually installed the Hadoop from the remote and run some command. First we should also set the .xml configuration, as we have already mentioned earlier. And when you type the command jps, it will show all the Java process running on the machine. And in the next, we have created a user directory, and then inside the user directory we have created another SD user directory. This is all happening in the Hadoop distributed file system. And in the next, we have actually uploaded the local password file from our machine to the SD user inside the SD user directory. So this is just a simple example of SDFS system. That's all. Thank you.